Hey there! Welcome to this explainer. Today, we're tackling something pretty mind-blowing: the invisible forces that literally power our entire world. Now, if you've ever sat in physics class and felt a bit overwhelmed by electricity and electromagnetism, trust me, you are absolutely not alone. It's tough, right? Because we can't actually see electrons flowing through a wire or magnetic fields pushing things around. But today, we're going to make all that invisible stuff visible together.
Here's our game plan for today. We'll start with the magic of static electricity, then explore circuits using a water park analogy, dive into magnets and invisible fields, see how electromagnetism works in everyday tech, and finish up with the national grid journey.
Okay, quick question to get us started. Think about your phone, or maybe your smartwatch. How exactly does it charge just by sitting on a little plastic pad, without a single wire plugging into the device itself? Well, stick with me, because by the end of this explainer, you'll know the exact physics making that happen.
Let's jump right into part one, the magic of static electricity.
What is so fascinating to me about this is that we're looking at the exact same physics operating in two completely wildly different ways. Think about lightning. It's nature's massive, terrifying static spark, right? High up in a storm cloud, particles are just furiously rubbing together. This creates a massive separation of charge. The top of the cloud becomes positive and the bottom becomes super negatively charged. Once that potential difference gets big enough, the air suddenly conducts electricity and boom, a giant spark leaps to the ground. But then, look at car spray painting. We have actually taken that exact same untamed force of lightning and engineered it to perfectly, smoothly paint a car.
So how do we do it? These 4 simple steps show how we guarantee a beautifully even coat of paint, even getting right into the tricky corners of the car frame. Step 1, the nozzle of the spray gun gets a positive charge, which makes all the paint particles positively charged as they leave. Step 2, because all those paint particles have the exact same positive charge, what do? They strongly repel each other. This forces them to spread out into a perfectly fine mist. Step 3, the car itself is hooked up to a negative charge. And finally, step 4, because opposites attract, those positive paint particles are powerfully, magnetically drawn right onto the negatively charged metal. It is a brilliant real-world life hack using static charge.
All right, moving right along to part 2, circuits in the water park.
Since we can't literally see electrons zipping around a circuit, this water park analogy is going to be your absolute best friend for your exams. Just imagine a giant water park. The battery, or the voltage, is the massive water pump. It's what provides the initial push, or potential difference, to get everything moving. The electric current, which is the actual flow of electrons, well, that's the flowing water itself. And resistance? That's any narrow section of the pipe, or maybe a big water wheel that takes energy to turn. It restricts how fast the water can flow. Thinking about it this way makes invisible circuits so much easier to visualize, doesn't it? Now, conventional current always flows from positive to negative, and how we actually build the path for that water determines how our gadgets work. We essentially have 2 choices. A series circuit gives the current just one single path to flow through. Everything is wired one right after the other. This setup is great for something like a light-dependent resistor, or LDR, detecting light levels to trigger a single, simple response. But a parallel circuit, that gives the current completely independent paths to travel down. Think about your hairdryer. You want the heating element and the fan motor to operate independently, right? You definitely don't always want full heat just because you want full fan speed. A parallel circuit is what allows those components to be switched on and off totally separately.
Okay, let's jump into part 3, magnets and invisible fields. If you grab a piece of magnetic material, like iron or steel, you can actually turn it into a magnet just by stroking it with an existing magnet. What you're physically doing is lining up tiny, microscopic internal regions, called domains, so they all face the same way and behave like one giant magnet. But not all materials are created equal here. Iron is what we call an induced magnet. It's incredibly easy to magnetize, but usually only while another magnet is close by. It loses its superpower pretty quickly. Steel, on the other hand, is stubborn. It's much harder to magnetize initially, but once you do, it becomes a permanent magnet. It stays magnetized even after you take the first magnet away. Oh, and pro tip, if you ever want to purposely ruin a magnet, just hit it really hard with a hammer or heat it up. It scatters all those little domains back into chaos.
Here's something wild. Whenever electricity flows through a regular wire, it naturally creates an invisible magnetic field around it, shaped exactly like a cylinder. But how do you know which way that invisible field is spinning? Well, try this physical life hack right now. Seriously, hold up your right hand, pretend to grip a wire. Point your thumb in the direction the electric current is flowing. Now look at how your fingers naturally wrap around that imaginary wire. Boom! Your fingers perfectly trace the exact direction of the invisible magnetic field. We call it the right-hand grip rule, and it is a total game changer.
Which brings us to part 4, electromagnetism in everyday tech. This is where it gets really fun.
Now, to figure out the complex interactions between these invisible forces, physicists use Fleming's left and right-hand rules. I know, it looks a bit like you're throwing complex hand signals, but it's incredibly useful. Your thumb represents the force or motion. Your first finger represents the magnetic field, and your second finger represents the current. By aligning these 3 fingers at right angles to each other, you can predict exactly how a motor will spin or which direction a generator is going to push electrical current.
And speaking of motors and generators, if you open them up, they look almost structurally identical on the inside, but they operate in perfect reverse. A generator takes physical motion, spins it inside a magnetic field, and forces an electrical current to flow. It makes electricity. A motor does the exact opposite. You feed electrical current into a wire that's sitting inside a magnetic field, and those interacting fields create a physical force, giving you motion.
Now, if you're using a generator to induce a potential difference, meaning you're forcing that separation of charge to get electricity flowing, you obviously want as much power as possible. To induce a stronger current, you just need to remember these 4 physical tweaks. You can spin the coil faster. You can place a soft iron core right inside the coil. You can add more loops of wire to your coil. Or you can simply use a much stronger permanent magnet. Moving a magnet and a coil of wire relative to each other to generate power is called electromagnetic induction, and those 4 tricks are how you supercharge it.
So what kind of electricity does that generator actually spit out? It produces alternating current, or AC. Because the coil is spinning in a continuous circle inside the generator, the induced current flows one way and then constantly flips and flows the other way. This is the stuff that comes out of your wall sockets at home. Compare that to direct current, or DC. DC flows continuously in one single direction, kind of like a steady river. That's the type of power you get from your AA batteries or solar cells.
So let's bring this all back to your bedroom and your kitchen. How does this physics actually help you live your life? First up, your headphones. Inside every single earbud is a tiny magnet and a coil of wire. When the AC music signal flows through that wire, it creates a changing magnetic field that rapidly pushes against the permanent magnet. This motor effect vibrates a tiny paper cone, pumping out the sound waves you hear. Amazing, right? And what about that wireless charger we talked about at the very beginning? There's a coil of wire in the charging pad and another one inside your phone. The pad creates a changing magnetic field that literally reaches right across the air gap and induces a current in your phone's coil. No wires needed. Finally, induction hobs in the kitchen. An AC current in the hob creates a constantly flipping magnetic field. When you put an iron or steel pan on top, that field induces electrical eddy currents directly inside the metal of the pan. The pan's own electrical resistance causes it to heat up, cooking your pasta, while the glass hob underneath stays totally safe and relatively cool.
Okay, let's wrap this up with part 5, the national grid journey. Let's zoom out.
400,000 volts. That is an absolutely massive number, and it represents the voltage running through those giant towering metal pylons you see when you drive across the countryside. The national grid steps up the voltage from the power station to a whopping 400,000 volts. But why? Simply because trying to push electricity across hundreds of miles at a low voltage loses a ton of energy as heat. By stepping it up to an incredibly high voltage, the electricity can travel super efficiently without wasting all that power.
Let's quickly trace this journey step by step. We start at the power station, spinning those giant electromagnets and generators. Next, step up transformers, crank that voltage all the way up to 400 kilovolts. The electricity then travels efficiently across the overhead pylons. But listen, we obviously cannot have 400,000 volts blasting into your bedroom wall socket. That would be literally disastrous. So right before it reaches your street, it passes through step-down transformers at local substations. This safely drops that massive voltage all the way down to a totally usable 230 volts. That's the safe level that powers your home, your TV, and your chargers.
So look around your room right now. Where are the invisible electric and magnetic fields working to make your life easier this very second? Is it your laptop charger, a Bluetooth speaker, maybe a desk fan? Once you really start looking, you realize this invisible physics is absolutely everywhere. It's been an absolute blast making the invisible world of electricity and electromagnetism visible with you today. Keep exploring, keep looking at the gadgets around you, and most importantly, keep asking questions about how they work.
Catch you next time.